try again. So let's start problem 3. Now, it's geometrical, so I don't think much computation will be needed, particularly not much algebra, which pleases me no end. So, the 4 points of order 2 on an elliptic curve. I think we already have had that in the text, that so we have 2p equals the point at infinity, and there are only 3 of order exact 2, namely the roots So we have 3 distinct roots, and at those roots, the curve will look like a parabola. And now if the coefficients are real, a real and a positive, then it will look like this, and at the roots we have vertical tangents, and they intersect the curve at infinity. So that's A. Now B, 9 points of order 3. Now, to find a point of order 3, we have to have a point so that twice the point is the reflection in the x-axis. So we need to have 2 x point y equals x minus y. Or at least they should have the same x value. Now I'm working on a symmetric. Oh, it will be symmetric, right. So that means that when we take the tangent, let's say we take the tangent here, it will intersect up here, so the result is down here. So we need a tangent that only cuts in the same point, and that means that it must have contact of order 3, which means it's a point of inflection. And we do have 2 points of inflection here, somewhere here. This is a poor drawing, but I hope you get the drift. So we have a contact of order 3, and then by Bezout's theorem there are no other intersection with the curve. And that means that the sum lies down here, and those 2 added is the point of infinity. So on this curve I can find 2, and then I know the point at infinity. That's 3 points. Now there are 9. So the others must be hidden among the complex numbers. Now if we go back to the complex plane with the original lattice, Then we have the lattice points. And if we divide that by 3, then we get the points here. So that when we multiply them by add them 3 times, we get a lattice point. So we just have to map them back to the elliptic curve. And that means that we actually have 1, 2, 3, 4, 5, 6, 7. Oh, here's only 1/3. We need another one up there. And another one up here. 2 omega 1, 2 omega 1 plus 2 omega 2. Yeah. So this have all 9, and then I don't count that one. So there are 9. So I can't come that any closer. Now 12 points of order 4, which are not of order 2. So geometrically we have to find somewhere where we have a tangent going through these points. This one I can do. So if we choose this point, then if we go up here, choose a point where the tangent goes through this point. So we are now in the XY plane. So this point will have order 4. So the tangent goes down here, so that's 2p. And then when we, of course, we could just add this to itself, that gives 4p. But if we add these two, then we get the opposite, 3p. So they of course come in pairs. And then we can make the same drawing here, which gives 4 squared, and then we have to subtract the 4 of order 2, or the 3 of order 2, and the 1 being the unit element, which gives 12. I hope that's what it says. The 12 points. Good. Yeah. Now, the associative law of addition. Oh my God. So let's take 3 points, and since they may be whatever, A, B, C. A, B, C. Now first we add A and B. It intersects here, so this is A plus b. And then we add a plus b and c. It intersects here, meaning this is the sum. Right. Next we add b and c. It intersects up here. So b plus c is down here. And then we have to add a with b plus c. It intersects here, so it's up here. This is not a correct drawing, so it's terrible. Maybe I should do it on Maple with some examples. Now, these points have to agree. Yeah. A plus b is here. So I went through the wrong point there. I should have gone through this point and then ending somewhat closer to the right answer. Oh, so this one goes down here, where this one, a, b plus c, should go through as well. So this one and this one should go through the same point. A plus b plus c. So that means that these 2 points, the yellow one, a plus b plus c, should go through the same point as as a plus b plus c. And then maybe we should forget about going to the other side. No, we have to do that. So let me just write that down. So a plus b there, and then b plus c, down there, and then a and b plus c. I don't think I can come any closer to it at all. So this is just a geometric formulation of the associative law. So says about a certain configuration of lines joining points on the elliptic curve. Yeah. So I leave it at that.